VDL VDL systems, right? This is basically communication link between air and the ground. Correct. So there are various standards in which the communication will take place, and there are various generations over which this technology or this particular technique has been evolving, right? So because of that, uh, basically it uses the specific type of data uh, for using which using this VDL systems itself, the pilots can change the routes, speeds, altitudes, right, as and when needed, with very in the sense, with the ease of what you call, right, everything that is available at their hands, they can actually try to modify those values which are without VDL system. This would have been very difficult, right? Something like you can change the route very quickly, right? Or when actually when the uh, say the aeroplane is at 30,000 feet above ground level, right? And visual communication is not, there is nothing which is visual, right? So visible, nothing visible at that height. So a specific type of communication technique is required, right, which is dedicated for this, right, for this kind of situations. So basically the aircrafts or any other normal aircraft or any other type of aircrafts, right, they will communicate with each other, right, using specific VDL technique. Okay, so generally, the general structure of this kind of communication happens in the following fashion. Let's try to write one block diagram representation for this. Okay, so let us assume that there is aircraft number one, and we have another aircraft at a different location. Could be aircraft number two. Okay, so basically, this communication uses a specific application for that. So there are varieties of applications that are available, something like ACARS or ATN, right? Multiple uh, softwares are available, right? They are something like they are used by the individual manufacturers, right, for their aircraft. Like Boeing might use ATN, and if say we go to any other like Airbus, it may be a different ACARS software, etc. You have various softwares available. So each one use their own, we can call, application. So there is one application for aircraft one. There could be a different one for this right. Followed by we have the specific protocol that needs to be used for communication. Uh, Maybe let's say right now we are trying to communicate from aircraft 1 to aircraft 2, or aircraft, this is air to air. And if we are considering an example of air to ground, then the communication will be between the aircraft and the ground, for example the ATC. Okay, traffic controller. Fine. Uh, Let us try to have. Uh, okay, let's see both the types of protocols. Commonly used two types of protocols. I will show you here. Right. This there is a protocol. I'll call it as a protocol one. Let's go to the details at a later stage. Okay. I'll say protocol one. This uses a different one. Protocol number two. So they are going to use this. Okay. Uh, Now, the protocol 1 and protocol 2, we differentiated because it's not the same protocol. Again, it depends upon what application, what type of application, and maybe the varieties of aircrafts, etc. It actually varies from one to one. Now, basically, I'll write here. So this protocol could be something like what type of data it is handling, what type of data you are actually trying to send, uh, or what type of communication you are using. Maybe I'll just write as a different block here. Uh, First one is the character oriented. So we know that in a communication protocol we have something called as a subnets, right? It's a part of the network, right, which helps you in communication, right, in implementing the protocol for communication. So character oriented subnets are the fundamental features of this kind of protocol, and actually there is a name for that. So but since we have never discussed about any other details of what protocols, right, what are the protocols used, etc., I didn't bring the name. It's actually B22 is the name of the protocol, but anyway, let's keep to protocol 1. Whereas the protocol 2, it's actually a ATN type of aircraft will use this. So there is a protocol name called as uh, ATN protocol, right? That's what we are looking for in the second this thing. But they are identified as bit oriented. One is a character oriented, and the second one is bit oriented subnets. They are used in this the second kind. Okay, that's right. Now the ATC comes into picture, right? Let's say we have a bigger block. Okay, I'll draw that block later. Let's say the communication uh, enters, right? So through this, now the communication is established between this aircraft and the ground, right? So there will be uh, a stack that is internally present in the computer of the ATC, right? So that is denoted as, let's simply write stack here. So there will be, this part is actually inside the ATCs, right? So this is a computer stack for the data, right? There will be another simple stack on the other side. Right. Then followed by you have to use a gateway, right? Because the data which come faster will be saved in the stack, right? Later on, it will be brought into the computer, right? Computer's memory for processing, right? For that reason, you will have a gateway on both sides. So irrespective of what type of protocols you are using, your architecture remains pretty much same, right? Followed by the communication selection applications that's actually running on the background of the computer will come into picture now. So this is so uh, this is how the communication will take place. So this is coming to the stack, then comes to this, then comes to this. Similarly, this side also it comes to this, and it enters into this, right? So again, you have some of the protocols that run on the background. So here this is actually connected to, it's actually two-way, the ATC automation. That process will also run simultaneously. So it is connected to that. Now, uh, this whole part, what we see now, is actually the ATC. Change the color. So this is, other than this, everything is in the aircrafts, but this is a ATC part. All right. So we have varieties of communication that can come from an aircraft towards the what do you call, towards the ATC, from the aircraft to ATC. Right. So whenever now let us try to uh, compare, right, the two types of protocols that we saw so far, right? So the first one, let us say both aircrafts are both aircrafts are flying at the same speed, at the same height, maybe different directions. All right. So they want to send a message saying that, okay, uh, we are climbing to this level, we want to maintain the speed of this much, etc. There will be a reporting process that's happening continuously between the aircraft and the ATC. Let's say you want to send the same thing, same message, right? Both wants to send same type of messages. So the first type of aircraft which actually uses, right, we can see here, I'll give the name over there so that it's easy for us to recall and remember. So aircraft 1, I'll write, it's actually referred to as the ACARS. This is ACARS, and the second one is the ATN. Let's say this is ATN type. It because it is uh, there is a differentiation because of the type of protocol they are using. I'll just write the protocol over here. This is something like B22, right? And the protocol 2 is ATN, right? So now let's go further and let's try to write the ACARS aircraft. This uses that let's say there is a message to be sent. Normally, any message that you want to send, right, uses that protocol. So this protocol converts the message in bits, bit format, converts that into hexa. So that's why you can see that it's a character oriented character, in the sense you have 0 to 9 and ABCD, right, etc. So that uses the characters, right? So hexa uses characters as well, not just bits, right? Assume that both messages are same, right? That both aircrafts are sending the same message, but the way of representation is different for this A cars, as well as when we go for the ATN, right? Let's say we have a message, and you always try to use the ATM protocol. So this keeps the message in the bits format, right? You keep only zeros and ones. That's the binary type of encoding. Okay. Now, uh, the other difference when it comes to this kind of communication is, right, in terms of the protocol data units. That's PDU is one important detail. This is the protocol data units. In the sense, we know that data is represented in the form of characters for the first type, and the second type is using the bits in the format. That's fine. But let us look at the PDUs, how many are present, and what type of representation, what type of arrangement happens in one data. Maybe you can call it as a packet, right? It can be a packet, or uh, you can get varieties of the various types of data representation is also possible, right? You can consider the smallest piece of data that you can send as a packet as well, like networking, right? So for the first one, right, whenever we use any character oriented protocol, the general representation of the PDU is as follows. So maybe we can have this. So the first few bits will be the protocol itself, right? So this is protocol, followed by, let's say, I have three more fields, right? In this field, we use 8-bit ASCII representation for everything that you enter in these fields. Whereas if you go for the bit oriented, right? This is character oriented, the first one. And if I go for the bit oriented, let me assume the similar scenario here. We have three fields, okay, and this is again the protocol details comes into picture, and these fields you see, actually they may not be of the same size. I'll show you the different sizes as well, right? So here, the previous one, you see the size was fixed, 8 bits at each location, right? For each of the field you use 8 bits, but here it is random. This is arbitrary sized bit fields. So each of these fields are different in terms of the size, right? What is the size that we try to, what do you call, allocate is completely different. Okay, now you see, this VDL systems are actually divided into type 2, type 3, and type 4. There are various types of VDL systems that come into picture. They actually provide you, right, the various types of communication at different stages of the flight. Okay, for example, let's see. So the okay, I'll write this as okay. This is using VDL systems during flight. So at different stages of a flight, right? Like starting from uh, the initial phase where the aeroplane would have been parked, and from there you call it as a taxiing, and you bring it to the runway, right? That's one phase. Then the second phase could be the takeoff, right? Once you take off, then the next phase begins. The third phase is departure, right? So you have there is a takeoff and next stage until you reach a certain pre-designated height. It's a departure phase, right? Then that means you reach a height, you set your direction towards the destination, and that phase is called as the en route. Okay, en route. And as you come closer to the destination, say 50 kilometers or 100 kilometers away, right? Yes, so that is called as the fifth phase of communication called approach. All right, you establish a firm communication between that destination ATC and you approach. Okay, then once again, uh, all the way coming down and touching the runway, and until you come to halt on the runway, that is called as a land phase. And once again, the last phase comes as a taxiing phase. So these are the different various phases. Okay, that various phases of communication. Even though what we discussed was what is happening with the aeroplanes. Mechanism, right? But still, these are the same terms used even for communication, right? Communication is also in taxiing phase. Communication will be in the takeoff phase. Communication in the departure phase, en route phase, approach, land, and taxiing phase. These are the names even given for it. Yes, absolutely correct. So, because of the various information that needs to be processed during different phases of the flight, right? So, and they are completely different. Now you will come to know how they are different, right? So, let's just look at the names and what type of VDL systems you are using. So, the first phase could be the taxiing, right? When you do that, you use the VDL 2, 3, and 4. Okay, the same thing is good at even in the takeoff. Takeoff also uses the VDL 2, 3, or 4, right? And uh, this is true. You can actually choose VDL 2, 3, 4. I'll write in a different way because VDL 2, 3, 4 are used in many of the cases. So the taxiing, I'll write all the phases where you use the VDL 2, 3, 4. Okay, so taxiing, then even the takeoff, okay, and departure, followed by okay, en route is not going to use this. That uses a different one. Okay, departure, then the approach, then land, and once again the taxiing. Anyway, taxiing has already been written. So all of them are going to use the VDL 2, 3, or 4, right? And en route is the middle phase which comes between the departure and approach. Okay, this if at all you are going to do a communication in the line of sight communication, if you are using, for example, between aircrafts, like there is one aircraft going and one more aircraft flying nearby, right? If there is a line of sight, then you can go for VDL. Okay, VDL if LOS, line of sight. At the same time, using the en route, you are going to use the SATCOM. And another technique that is called as HFDL, we'll see this the later stage. So if it is non-LOS communication, right? From the aircraft to a faraway ATC, which is not the line of sight uh, way of communication. Now, so what are the information that you are supposed to actually supposed to send or receive during each of the phase? That varies, right? Because of that, you have these variations coming into picture. But you can see that VDL is most of the time it is VDL, right? That's the specialty of VDL. VDL has been designed for this purpose, right? Between aircraft to ground or aircraft to aircraft, we can see that. Now, let's say during the taxiing, uh, what are the types of information you are going to send or receive, right? So this is from aircraft. From aircraft, the messages could be simply a link text. And then maybe you have to update the clock update. Then you need the information of fuel, or it may be the crew info. If there is a delay, that reporting something that is happening. And when you move out, this is a out message, etc. These are the messages, right? That normally from aircraft to maybe the ATC, or right, some sort of communication that is right. Then this is to the aircraft, right? So the pre-departure checking and air traffic information systems. Then you also have to send the details of the weight or the balancing. Then you have to specify the speeds. So it's in aerospace or aeronautical terms, it is V speed details, followed by what is the plan of flight. So I will write flight plan, etc. Right? Will be these are the messages normally that is from the aircraft and to the aircraft, right? Then during the even during the takeoff, right? Most of these messages, right, will keep coming or going, right, from the aircraft and to the aircraft, right? So taxiing, as well as I can write the same thing happens with the takeoff, right? It's same. Whatever we wrote earlier, you can simply say that, okay, most of the messages will be followed. Then, right after the takeoff, then we enter into the departure phase. In that, from the most common message that will be sent is the uh, engine status, right? So to uh, aircraft, it is the light plan, and it's an update. Only if there is an update, normally this is used. Otherwise, the most common message is weather. Weather update, right? This is during the what you call departure, right? Then the aircraft attains certain height, changes its orientation towards the destination, right? It marks its path. Maybe mostly you can even the pilots must may use even the autopilot or something like that. Okay, but you see everything that is communicated. Uh, Now the messages are slightly different than what uh, has been okay. What was being used so far, right? So let's go to the next phase, that is en route. So from the aircraft, we get the following, right? The first one could be the position report, right? Then, right. So current weather of that location will be responded back to the ATC from the aircraft. That is the weather, current weather situation. Then ETA info. This keeps on changing, right? In the sense, what is the estimated arrival time at the destination keeps on changing because, right, this is a parameter which changes, which actually depends upon many other parameters, like what is the current speed, right? Will the same speed is maintained throughout or not, it etc. Right? So it also includes the delay associated with. Then there may be a request to make a communication, that is voice request. Then definitely engine and maintenance reports. Engine report, which includes the maintenance part. All right. Then let's say what are the messages coming to the aircraft, right? So this is coming from ATC and ATC clearance. Whenever a flight, the path of the flight goes through various countries, right? There needs to be a clearance that has to be given at the moment when the flight enters into their zone, right? So that's the one. Okay, so clearance, and if there is a path change, right, due to some reasons, you need a re-clearance. Yes, correct, right, correct, right. So that's the one thing. Again, you need to update the weather weather status and the ground request. Some request that is coming from ground to the aircraft. Okay, request, etc. will fall under this case. Now, let's say you are actually approaching the, you are in the approach phase, right? From the aircraft, you may send what is called as a gate request, right? Then the estimated time of arrival, right? Engine information and maintenance, right? Followed by the messages that are sent to aircraft is where you are going to land, right? Details of that and where you are going to park. So the permission, gate permission, and it actually includes even the connection between that particular gate. And once again, you have to receive ATIS information system from the air traffic, right? And the further details, if details that are required to be given to the passenger and crew messages. Okay, then we enter into the landing phase, right? Landing phase is pretty much similar to the approach phase, right? Whatever that is pending in the approach phase will be carried over to the landing phase, so it's going to remain same. Then we go for the taxiing phase, right? So once again, you are trying to send the in message, right? This is on aircraft because tax during the taxing, anything there will be no communication no message to be sent from ATC to this one aircraft, because everything would have been done in the until the land phase and approach phases, right? Everything would have been done, right? Which particular, like if you have multiple runways, which runway, what is the path using which you will go to the particular gate, etc., will be already right sent to the aircraft. So now nothing to aircraft, only from aircraft. Okay, so you send a in message, you pass the fuel information, in the sense if you request a fuel, it's if it is like a technical halt, then you require just for fuel uh, refueling, right? That's the request. Then even if you want to send something related to the crew messages, then the fault data, right? This will be sent. Normally, the fault data will be maintained by a central computer in each and every what you call every ATC. Okay, so that is right. The message. Correct. Correct. Yes. Yes. True. 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 So that message will be passed on to the central computer of the whole ATC system, right? Whenever an aircraft actually lands in a particular airspace. Okay. Now, so let us see the basic difference. We saw that there are various modes of this VDL. So let's try to write this. So if in mode 2, so can use any type of either type mode 2, mode 3, or mode 4 can be used for the communication purpose, but some differences. So what are the differences? Right, we'll see. So the mode 2 uses the CSMA technique. Okay, so that is carrier sense multiple access, right? It actually, you are trying to sense what type of carrier has been used, maybe dependent on the frequency, right? And this basically mode 2 is used when, right, you want to have only data, right? If the incoming message or outgoing message contains only data, no voice, there's no voice communication happening, only the data, right? Some message is sent, maybe it can be a text message, or it can be a visual display of something, right, on the screen, etc. If you want to do that, that is called as data only, then you use mode 2. Okay, so this, the capacity, or the capability of mode 2 is to carry only data, it cannot carry the voice, right? Then the modulation used is the 8 PSK, differential PSK. So I'll write differential 8 PSK at a specific frequency of 25 kilohertz. So this is the specification of mode 2. So I can choose mode 2, right? Provided this is okay for me. I can use 8 PSK. I just want to send the data only, right? So because the frequency remains same irrespective of what mode you use. So the mode 3 uses the TDM. All right, so this is time division multiple access, right? So you can use both data plus voice. Again, you use differential 8 PSK. With a channel bandwidth of 825 kilohertz. So then we go for the mode 4, right? There is a slight modification in the TDM. This is called as STDM. So STDMA stands for self-organizing TDM, right? So the time slots actually are not fixed. You can actually have a small variation in the time slots, right? So that's the self-organizing. This uses only data. So this the modulation technique is a FSK modulation at 25 kilohertz. Okay, so now coming back to this, let's see where the techniques are developed, right? So this is the mode 2 was originally developed for ACARS type of aircrafts. It's actually a specific name for the aircraft. Okay, it's a like a what do you call? One second, let me. I'm not able to recall the full form. I'll get back to you on this. But it's remember like it's like a name of that aircraft. Okay, aircraft. One is one name is ACARS aircraft, and you have the aircraft names such as ATN like that, right? So they're known by their names like this. Okay, but anyway, I'll try to find out that for sure. Okay, and the second technique is actually this is the mode 3 is basically the US program, right, for the video communication, right? And the last one is a Swedish design. So, so the various phases are developed at various locations, right? But they are standardized worldwide so that we can use it. Now, if at all we want to have the communication, right, for say, let's say we want to use the VDL system, correct? So what are the frequency, right, at which you can send, right? That is predefined. Okay, for example, let's see, I want to use the voice channel. My intention is to use a voice channel. I'll try to draw a single diagram for this. Let's see. Okay, so this I'll write it as, okay, let me have, okay, so in this, let me divide this into four. So first one is the voice channel. Okay, this is the actual design part, right? What you are supposed to design, right? When you are trying to communicate, what you are supposed to design. Okay, so the first part is for the voice channel, right? So in order to design a voice channel, let me, okay, let's say we have two different channels available for us, and each channel is to be 25. Okay, this is 25, 25 on the left and the right of, right, and I have totally, this is one 25 kilohertz phase, and this is another 25 kilohertz. Right. Now, depends on what is the application and how much bandwidth you need. you actually can divide this total space, this is the total 50 kilohertz space, out of which we know that we have assigned already a 25 kilohertz. We have split this into 25 into 20, 25 and 25. Okay, so we the 125 kilohertz is used, right, completely for using the DSBSC suppressed carrier AM modulation. Okay, and uh, this is one complete channel for what you call analog voice communication. Right. Again, you may not require the complete 25 kilohertz bandwidth for some cases. Okay. In such cases, what you can do, the remaining 25 is also used. It can be used, but you see that it is something like it is divided into three parts. Like this, right? Each of this subdivision, what you see here is once again the DSBSC, double sideband suppressed carrier. Okay, right. So again, you can use the analog voice over here, but this is something like only 8.3 kilohertz. 8.33. So overall, this becomes 25 kilohertz, right? And you can send the analog voice even any of. But you see the bandwidth is less over here. You can use either of these four channels. That is the first part. That's the channel design, right? You have to design the channel like this. Okay, coming to the mode 2 now. So this is mode 2 and this is for mode 3. Okay, this is mode 4. Okay, now again we have the 25 kilohertz bandwidth allocated for this, because we already know that the width is 25 kilohertz. This is 25 and this is 25. So this is mode 3, mode 4, 25 kilohertz, 25 kilohertz and 25 kilohertz. Right. Now, similar to this, we can rewrite the various modulation scheme. This is differential 8 PSK needs to be used. D8 PSK, differential 8 PSK. Right. Then the multiple access techniques can also be embedded over here like this. So I'll write, I think this was CSMA. Then we have TDMA and STD. Right. So normally this is data. Right. So here the data plus voice. So now when this voice is used, correct, you normally use these three channels. Okay, but only when you send without data, if you want only voice, then you use this, because you get more bandwidth over there for the message. Okay, so this is, yeah, Correct. Yeah, correct channel, right? Bandwidth according to that. So if it is data plus voice, you use data normally and use one of these three channels for communicating. At the same time, you are using mode 3 and you are sending only voice, you can go for this. Then this is again the data. Is it okay? So you can see that depending upon the various types of message that you are supposed to send or receive, right, at various phases of the uh, flight, right, various modes have been created in the ADL, right, and each of the modes use varieties of what you call modulation schemes, varieties of the multiple access schemes, and they are supporting multiple types of data like data and voice. Right. So here the something like the video is not yet supported, right? And it is not required also, right? So the video part has not been included in any of them, right? Just because of the reason that it is not relevant as of now, and only either you need the data to be transmitted or received or the voice. So hmm, right, right. Correct, 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 correct. So because of all these reasons, you don't require the message that needs to be transmitted or received in the video part, right? So for those reasons, uh, other types of communication, maybe any other multimedia files are also not included here. Only the data and the voice. So the actually in this we have you can actually study more on this related to what type of satellites that actually are part of what you call this communication, because as you move closer to the ionosphere of the earth atmosphere, right? So you actually you have to face some more problems, right, in this communication. And the ground communication between to the ground is going to be difficult compared to the communication to the satellite. So in such cases, true, 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 right? So hmm, right, right, right. So very various parameters will come into picture, right? So there are a lot of propagation problems associated with the communication at very high frequencies, right? So it's because of environmental reasons, like ionosphere comes into picture over there, and it actually affects your communication. So also, as you told, the relative motion is also a another reason. At very high speeds, at a very what you call varying heights of aeroplanes, these are the various parameters using. So normally you do the communication instead of directly aircraft communicating to the ATC, aircraft will communicate to the satellite, and satellite will communicate to the no, satellite will actually include another ground base station. Like there will be a base station, because a satellite to what you call the yes, because that will be a well-established link, right, between the satellite and a base station at the ground. That is actually satellite communication. Separate channels are allocated for that, so no interference for that. That will be a very clear, very pure way of communicating. And from that ground station, or we normally call it as a ground earth station, you can send a message to required point, like the ATC. Okay, so like that's the next part of this, and over there normally we discuss what are the problems, how to overcome that, right, etc. Right, will be discussed over there. But anyway, just to have a overall idea of what is VDL system and how to go for its basic design, I think this diagram is sufficient.